this seems like a great time. I just want to say good morning and thanks everyone for joining us for another awesome webinar. We are incredibly excited to have you here this morning and really appreciate you taking your time to listen in on this. And I know you're going to learn an absolute lot about all things risk analysis related. Before I turn it over to MPR, I just want to, a few housekeeping things. If you have questions, please feel free to pop them in the chat bot, and MPR will be answering those kind of as they go. And make sure you're muted when you're not speaking so we don't have a lot of background noise. Really do appreciate, again, you joining us. And I'm going to go ahead and turn it over to Lanessa and Eric from MPR Associates. And just a little bit about MPR, they'll tell you a little bit more. But MPR is a fantastic member. They've been a member of the MassMEDIC organization for years now, and just do excellent, excellent work. And I know you're going to learn a ton. So I'll turn it over to them.
Super. Thanks so much, Rachel. So just briefly about MPR, we are a engineering and project management services company with a team of about 250 folks, engineers of all 31 flavors, you might say. Located usually at offices in Virginia, Massachusetts, and Connecticut. Of course, we're all working from home now with a handful of folks in our labs, continuing with projects. You might be wondering what MPR stands for, and that refers to our founders, Misters Mandel, Panoff, and Rockwell. They were the three lead engineers who worked with Admiral Rickover in the 1950s on the development of the first nuclear-powered submarine, the Nautilus, and founded MPR in 1964 with the goal of applying the systematic de-risking approach that was successfully used in that naval reactors program to other big engineering problems. And so we currently continue to work for the federal government as well as in energy and in healthcare. I lead the MPR's healthcare practice, so I'm Eric Claude. In our healthcare business, we work on strategic planning, product design and development, testing, as well as consulting around process and product improvements and things of that nature, where we do quite a bit of work helping our customers get to the bottom of problems that they're experiencing, and that's what we'll talk about today. My background is I'm an engineer, and for the better part of 30 years, I've been involved in various aspects of development for medical devices, diagnostic systems, and drug delivery systems. So happy to share some of our experience with you. And I'm joined by my colleague, Lanessa Erler. Lanessa, could you provide an introduction?
Sure. Good morning, guys. My name is Lanessa Erler. I've also been with MPR Associates now like 26 years. I'm a mechanical engineer by training, and I really sort of got my start doing a lot of test engineering, and that's how I got pulled into a lot of root cause analysis as somebody who could come in and design tests to test different hypotheses of root cause. I currently serve as the director of product testing in our health and life sciences group. And in that role, I kind of get into design assurance activities, risk assessments, and then also our V&V activities for both our in-house product development and for our clients.
Super. Let's go to the next slide.
Okay.
Great. So, so we're going to talk today about root cause analysis and really getting to the bottom of understanding what the problem is that you're trying to solve, which is a big part of the issue. Just by the way, this is a training that we use for workshops that we do with clients that we sort of repurposed for this webinar today. And let's get into it. If you could go to the next slide, Lanessa. By the way, we'll close with contact information for Lanessa and me, and if you'd like to reach out, we'd be happy to share a copy of this with anyone or address any follow-up questions. But we'll get into it now. So what we're going to talk about is, crafting a problem statement. That's sort of the first piece of this. How do you collect the facts to understand the the nature of a problem and get to the bottom of that situation? What are some techniques to evaluate information that you'll collect, and then how do you sort of dig through that and get to the root cause of a problem and prove that in fact that is the right answer. So a lot of frequently this process is employed around dealing with problems that have been experienced, but we also like to point out that used properly, this process is really effective at driving real sustainable improvement in products and processes as well. And we'll talk to that. Let's go to the next one. So what is root cause analysis anyway? So what we're talking about is a process. It's a process and a set of tools, and we'll talk about both of those pieces today. But it's a process for identifying the underlying causes of a problem, and that's critically important, because if you can't find those causes of the problem that you're experiencing, it's really difficult to develop an effective solution, right? So it's getting to the underlying causes, typically when something goes wrong, but can be used when things are going well as well. So we're going to talk about one set of tools. And by the way, what we're going to talk about today, the sort of basic fundamental tools and process involved in root cause analysis, similar concepts you'll find in other management systems, right? Like we've shown a couple of them here: total quality management, the DMAIC steps at the bottom. Those are also processes and tools that largely accomplish similar kinds of activities that we're going to talk about today. Okay, so how, what are the scenarios in which you find yourself in this situation, right? Lots of different kinds of scenarios can trigger the need to do this kind of thing, to do a root cause analysis. If you're in the process of developing a product or a device, and you get near the end into design verification or validation and start to experience failures, right? That now you've got to get to the bottom of why those failures happened and how can you fix those problems and move on. Obviously, field failures, recalls, customer complaints, right, also can be sources of initiating this kind of a process. And then, that's sort of very product-centric. On the manufacturing or operational side, root cause analysis is frequently a tool used to assess low production manufacturing problems or to support other operational improvements and initiatives. Also, typically, you'll find that from the quality management system perspective, this is an activity that gets kicked off through a CAPA process. Okay, so what is the process? This slide gives you a high-level overview of how we define the root cause analysis process, and we'll walk through each of these blocks today. So it's important to understand that this process is I'll say, generalized problem-solving approach. It's not specific to any sort of type of problem or management system, and it's scalable. It can be used for small problems and big problems. So, but it requires discipline. It requires discipline to sort of stick to the process, and impartiality, because we're talking about digging into issues and failures and problems, and it can often be the case that people can get defensive, right? There's a rice bowl kind of an issue that you've got to manage. So those are critical sort of attributes. It's often helpful to have a group that facilitates the process, right? That does not have a sort of a dog in the fight, if you will. And that's frequently sort of a scenario in which we're brought in to lead a root cause investigation. So let's go to the next one. Okay, so step one a problem has happened. What's the problem? Well, my product hasn't met, my requirements or my standards, or I'm getting, as we said, customer complaints or dissatisfaction, and we don't often see the actual problem that's happening. We see symptoms of the problem. We see some behavior that's happening that's unacceptable, right? So the first thing is to craft a problem statement that guides future activities. And when you start with this, identifying the problem, we have to realize that we may not have all the information that we need to accurately define the problem statement just yet. So usually when you start, usually this is an iterative process. And when you start, the problem statement might very well be an assumption or an opinion, might not be fully factual. Certainly there's a possibility that the way the problem is defined is clouded by biases. Often, we like to define problems in a way that is targeted towards a preferred solution, right? Because that's we like to solve the problems that we know how to solve, and often based on incomplete information. So I'll give you an example of where this has played out. We did a root cause analysis a couple of years ago for a customer that had a battery-powered surgical drill, and really interesting behavior happened with this drill, where the drill would be used, it would be set aside, and the battery would overheat, just on an intermittent basis, not every one of these devices, but just intermittently. Keep in mind, the drill's not being used, right? So there's like no way the battery ought to be overheating. Well, the way the problem in this case was defined was to say something to the effect of, there's an intermittent hardware fault that's causing the battery to overheat, right? The way that problem was defined made the assumption that it was hardware, that it was some electronic component that was failing and creating maybe a short circuit or something to allow the battery to overheat. What we found, though, when we got into it was, and our customer had looked at circuit boards for some of the devices that were experiencing these failures, trying to find the failed component on the board. Nothing. They couldn't find anything. So they asked us to get involved, and we looked into it, and long story short, we found that the microcontroller that was opening electronic switches to allow current to flow and the drill to operate was programmed incorrectly. And there was a programming flaw that was allowing this strange intermittent behavior to happen, which no one suspected, interestingly enough. But in any event, the real problem was very different than what the initial problem statement sort of led everyone to believe. Super. Vanessa, how about I turn this over to you for the next couple of things.
Sure. So as Eric stated, it is often an iterative process to properly define the problem statement. What your goal here, your final problem statement should be clear so that everybody can understand the problem. And then you also need it to be concise and complete. So you're trying to strike the right balance between brief and yet comprehensive so that you're encompassing the full problem, again, in a way that's easily understood. You want it to be factual, avoiding opinion or allowing bias to creep in, especially at the onset of all of these activities, because that bias can follow you all the way through. So it is an iterative process. It is worth the effort because this helps provide focus for all the subsequent activities. So what often goes wrong in this step of the process? The main thing often that goes wrong is it's skipped entirely. You'll often find that everybody thinks they know what the problem is, but everyone has a slightly different idea of what that problem is. So, keeping the problem statement clear and documented helps keep the team focused on the issue at hand. You shouldn't also, try not to pull in other related issues unless they really are likely to be symptoms of the main cause. You also want to avoid assigning blame, whether that's blame to a person or blame to a system or subsystem. You know, try to avoid predisposing your root cause at the outset. The next step in the process is to start gathering facts. So what you want to do at this stage is to cast a wide a net as possible to gather all the information that might be relevant. There are many sources to consider when gathering facts, but most root cause analysis start with pulling, usually you start pulling past failure history, interviewing personnel involved, and then gathering information, related information from industry and academic sources. So here's a list of potential sources of information. As you can see, it really kind of encompasses, you know, anything relevant in the design history file, device master record, and batch record, in addition to pulling information from outside sources like FDA databases and academic research, and, you know, other vendors and other industry sources. So interviews are usually a key part of the fact gathering process. There's just, you know, valuable information in the memories and opinions of the personnel who really live with this device, whether they're involved in design, manufacturing, or the use of the product. But with interviews, you have to keep in mind that you're dealing with humans and human memory and human personalities. So you have to be sensitive to the position of the interviewee and, you know, sensitive to the quality of the information that you might be getting. So in general, interviews are most effective like right after an event when the knowledge is fresh. It is also common and useful to revisit interviews later in the fact gathering phase. It allows you to confirm facts or to go back and ask follow-up questions. It's also a good idea to develop questions prior to your discussion so that you've thought through what you want to try to get out of the interview, what questions you want to ask, have some follow-up questions. And then whenever you do interviews, you definitely want to have some way of validating the responses to assure yourself of the facts. So keep in mind the information that you're getting is from human memory. It's useful to seek corroboration of those facts. When you're doing interviews, you need to be sensitive to the position of the interviewee. You need to, you know, be aware there might be potential for bias, or you know, maybe pressures outside of your control. You know, is their supervisor in the room? You know, can you interview them without their supervisor? You might be getting a slightly different story depending on who else is in the room. And then finally, I would, you know, recommend that you document all your sources and dates. That's, you know, really useful to refer to later, so that you can identify the source of any piece of information. So this, you know, as I said, it's a good idea to prepare questions in advance. This is a list of common questions to kind of spur that thought of what you should be asking. And then in interviews, you definitely want to consider the source, their experience, any biases they might have, or any sensitivities regarding blame.
Yeah, it's a real trick to you know, have a technique to sort of pull information from folks in sort of a non-threatening way. It's a tricky process. Similar with suppliers, right? So suppliers are often important to have involved in the process where there's questions around components and things of that nature. They often have important information to us, so we need to, you know, think about involving them in the fact gathering process. There's some challenges though sometimes that can be related to engaging suppliers. Sometimes if we're asking for really detailed technical stuff, you might have concerns around intellectual property or liability issues, and you just have to work through those. You might have to anticipate suppliers being dismissive, so you got to be persistent and prepared, right? So it helps to have some basic understanding of their processes, their issues, and so forth, and understanding the contractual relationship that your company has with suppliers and specifications and so forth is also important. The same kinds of things that we talked about just now in terms of asking questions and focusing on facts, not blame, is critical. But suppliers do often have interesting information, and a quick thing about specifications is that suppliers define specifications for components sort of in a certain way, and sometimes the way in which we use a component might put that in an environment where the specs aren't necessarily applicable entirely. So another root cause investigation that we did fairly recently had to do with a surgical system that included a weight measurement subsystem as part of this device. And our customer was experiencing design verification challenges around verifying the accuracy of this weight measurement system. And it had some load cells involved in the design of this device. And we were trying to assess sort of the overall error budget for this system and what that meant for the load cells and so forth. And what we found is that while the load cell supplier had defined specs around accuracy, sort of in an ideal situation, as applied in this system and in the particular environment, these components were not performing as specified. And furthermore, in talking to the supplier, we learned that they had other models of this component that would actually have been better suited to be used in this particular system. And so we were able to uncover that information and make some recommendations around that. So often suppliers can provide critical insights. Let's go to the next one. So what could go wrong with fact gathering, right? A lot can go wrong in this phase of fact gathering, which is why it's often iterative as you go into future steps. Sometimes you get so much information that it becomes difficult to organize, and when not well organized, a forest of information can be very difficult to navigate. You may be looking for information that's not retained, has been lost, you can't find it, or you're focused too narrowly, and you miss some peripheral issues that are pertinent to the investigation. Really important as you're collecting data to understand what information has been or can be validated versus what may be opinion or unvalidated information. That becomes very important. And the other, the opposite of being too narrowly focused is being too widely focused and wasting a lot of time before getting into the next sort of phase of this process. So there's a lot of judgment in understanding, okay, when have I collected enough data to move on to the next step, right? And we've included this quote, nothing more deceptive than an obvious fact. What may appear to be obvious at first may not necessarily be, reality at all.
Might not be true.
Right. Okay. So let's talk about the next step. Now that I've got a body of information, now what do I do, right? So now we're going to talk about ways in which you can organize and evaluate the facts that you've collected. And here we'll show a number of different types of tools that can be used. There's lots of different methods for doing this: timelines, flowcharts, graphs. The key is to use a tool that will help you look for patterns and inconsistencies. That's because those patterns and inconsistencies are going to help us connect the dots between potential causes of the problem and the actual problem that we're looking to solve. As we said, in going through this process, again, just very important to identify data that you have that's unverified so that you can later go back and verify if possible, and and capture your assumptions. As we've shown on this chart, you're going to do some evaluation here. You may get some insights into potential causes, and then you may well identify new data that you need to go back, right? So this is an iterative activity. So timelines. Timelines are a useful way to look for changes that happened leading up to a problem or an event, whether those are changes to a manufacturing process, material changes, or other changes within a supplier's operation, environmental changes, people changes, right? So you can map those things out along a timeline and look for insights that may arise from that perspective. Really, it's a matter of identifying sort of a logical sequence of events that allow you to hypothesize whether a certain event may be a relevant cause of the challenge that you're looking for. Here an example with regard to Benjamin Franklin, measured in terms of decades. Timelines might be measured in terms of milliseconds as well. And I'm reminded of another example of a root cause investigation we did that had to do with a diagnostic system that integrated some off-the-shelf cameras and other electronic components integrated in with a computer system. This system, from time to time, would freeze up in use in the field, and was a real problem. What we did was we said, well, I've got different elements of the system, different components. I've got a couple different cameras that are communicating via USB to the main controller system. I've got some motors and some other things that are happening. And we mapped out sort of a timeline of when I do a diagnostic test with this instrument, what are the various events that happen leading up to the completion of the analysis. And by mapping out the sort of sequence of events that happen on a very short time scale, we were able to identify when the camera was operating and communicating data via USB. That revealed itself as the source of the problem we were looking for. So it was helpful to map out that process from a timeline perspective. Let's look at the next one. So graphs, lots of different ways in which you can use graphs and other visual tools to illustrate the data that you have. And it can be lots and lots of data. This scatter chart is particularly relevant if you have manufacturing process data, say around independent variables that can be controlled in the process, and product quality attributes, right? So if I can plot, or a control chart that you see here, if I can plot product quality attributes versus some independent variable like temperature or some other process parameter, and look at those graphs, I may be able to identify places in which that independent variable, say temperature, if I have a temperature excursion, I can see the potential effect on product quality attributes that may be related to that temperature, right? So important to, again, identify data that is maybe suspect, maybe an outlier, keeping in mind the accuracy of the data that you have, how it was measured, et cetera. So there are lots of ways to plot data. Again, it's all about sort of looking for those patterns and inconsistencies. So, this is really where the creativity of the team comes into play. It can insights and inventiveness are important to be able to explore different ways of looking at the data, and no one approach is necessarily going to give you the answer that you're looking for. So I think we would suggest that trying different ways, looking at the information you have through different lenses with different techniques, and being sort of creative in that process can be very helpful. At the same time, it can be a real challenge. You have to be persistent. You want to win over the experts on the team, to engage them to help, and you'll find more questions, right? So you got to keep asking questions as you go through this process, and look for apparent inconsistencies that don't make sense. We like to use the term first principles when we're trying to understand a problem, and that's kind of like the basic sort of physics of a system that govern how it works. And physics don't cease to exist, and so if you can put the pieces of the puzzle together in a way that is consistent with the physics, with the first principles, that is very helpful in lending credence to one's understanding of the problem at hand. The other thing that you run into is sometimes you get into this assessment of results, and you find that there can be apparent facts that apparently conflict with each other. And how can that possibly be? Well, it turns out you can. It can be the case that you have factual information about a problem or a process, and two facts might appear to be in conflict with each other, but it could be that you have incomplete information. So there's other information that can be discovered that, in a bigger picture way, will make sense of those apparent conflicts. So, Lanessa, gosh, what can go wrong with this?
There's a lot of things that can go wrong. So one thing is, maybe you're not using the right tool to best explore the data and the relationships between the data. So I think it is important to try a number of different methods. As Eric said, this is where one area in this process where creativity comes into play. Another is, there's a tendency to focus during a root cause analysis solely on the failures and not investigating the conditions and situations that can lead to success. You want to keep in mind that the success, those conditions are what you're trying to recreate and control to. So I think there's use in examining those scenarios equally as to the scenarios that lead to failure. Another thing is that it's common, when we talk about unvalidated data, it's common for in an organization for one person's opinion, especially early on in a product's life cycle, to kind of get taken for fact, and then that fact can grow into sort of a long-held corporate belief that can go unchallenged. So all through this process, as you're organizing and evaluating your facts, you just want to keep asking yourself how you know what you think you know, and do you really know it? So because you don't want your conclusions based on facts that are not true. So next phase is to start identifying potential causes. And there's a lot of different tools available for this that can help you explore and brainstorm potential root causes. Methods that are commonly used are like event and causal factor analysis, the famous fishbone or Ishikawa diagram. There's methods like the 5 whys, and there's failure mode analysis. It's typical to use more than one approach to really explore this space, and definitely as you go through this, you want to document each potential cause that you discover for later evaluation. So here's a list of, I would say, common general causes of failure. So as you're going through a root cause investigation, this is a good list to review, just to see that you've explored all the different possible categories. So things like, conditions of use that were not included or exceeded the original design. Issues with material quality or supplier controls. Improper design, I think this comes up a lot with usability issues, where maybe it's not an improper design, but the design space was not completely understood at the outset in terms of how the user was going to interact with the product. In manufacturing, there's inadequate control of process parameters, or maybe a lack of understanding of what those parameters, the complete set of parameters. Inadequate understanding of the required processes. You want to take a look at maintenance practices, operating practices, and management practices as well. So one tool that we've used is event and causal factor analysis. So this is a chart that allows you to organize events and conditions that lead up to failure in a way that helps you identify the conditions without which the failure would not occur. So I find this useful because usually there's more than one condition that has to be present for a failure to occur. Otherwise, you would probably have seen it early on in the design process or the V&V phases of product development. So you can use these types of diagrams to highlight sort of the off-normal conditions. So in the example given here, there's a person who has sprained their ankle because they were walking in a parking lot and stepped in a hole. The parking lot was not lit, which was how they were not able to see the hole, and there were not any barricades marking the hole. So those are very clearly, causal factors. Why was the person walking in that parking lot? Commuting to work, but maybe they, left work late after dark, and that's another contributing factor. You would have to say, hey, is that a nominal condition, leaving late? Maybe, but certainly, the parking lot not being lit should not be the nominal case. So it allows you to kind of organize all of the different events and conditions that can lead up to a failure. Another method, you've probably seen something like this. This is the famous fishbone or Ishikawa diagram. There are a lot of different sort of flavors of this. Lean talks about the 6 M's, where you have method, Mother Nature, man, measure, machine, and materials. But this is really just another way of organizing the conditions that lead to failure in a way that lets you visualize the combination of things that have to exist to cause the failure. So, in this is an example of a missed free throw. In my case, the cause would be all about the method and the people. Other people more skilled than I, there might be other issues that would have a more of a factor in a failure to in a missed free throw. So it basically, but you see, it allows you to not only identify main causal factors, but also with the branching, you can explore and document contributing factors. So here's a sample diagram. These are things to think about with people, skills, training, their motivations and biases. With the environment, you want to look at noise, lighting, temperature, humidity, those kinds of things. So this sort of is a good starting point when you're laying out these diagrams, things to consider for each of the different branches of the diagram.
Yeah, really useful tool. I'm a big fan of that Ishikawa type of a diagram for a visual presentation. If we were all in the same room together, I'd ask the audience how many folks have had experience with this 5 whys technique. it's interesting. The point is, keep asking why things are the way they are, to sort of dig to the next underlying issue, or the next causal event. And this is sort of a fun little example of how that plays out, right? So you see the fellow on the top left-hand side of the screen is pretty unhappy that he's got a flat tire in his car. And why does he have a flat tire? Well, the first why says, okay, I'm looking around and I can see there are nails on the floor of the garage. So clearly that's the problem. But if you ask why again, you might see why are the nails on the floor? Well, I look on the shelf and I can see the box that the nails are supposed to be in is split open. Well, why is that? Well, the box got wet. Well, that's unusual. Why did the box get wet? Well, rain came. I can see, rain has come through a hole in the roof. Well, that's not supposed to happen. So why do I have a hole in the roof? Well, there's shingles that are missing. So if I want to keep boxes of nails from opening up and spilling on the floor and giving me flat tires, maybe the answer is, yeah, I need to pick up the nails that are on the floor today, but I probably ought to fix the roof so it doesn't happen again in the future. So it's really a matter of continuing to pull the thread or drill down to get to the bottom of things. Let's go to the next one. So a couple of other tools, fault tree analysis is a way to illustrate potential causal factors that lead to an undesirable result. Can build on the 5 why technique. This is an example of what a fault tree might look like for a situation in which an incorrect dose of insulin is administered. So you see, that's the top level, bad thing that happens. What are the potential things that contribute to that undesirable outcome, right? And you see that's broken down at the next level into 3 potential high-level causal factors, right? So I may have an incorrect glucose level that's been measured, or I may deliver the correct dose but at the wrong time, or I may deliver an incorrect dose because the delivery system didn't work properly. And at the level below that, you see each of those causal factors broken down at a further level of detail. So in the case of an incorrect measurement, could be the sensor didn't work, or the computation was incorrect, and the computation could be incorrect if I had either glucose algorithm error or the fundamental math was programmed incorrectly. So this is just a useful way to present the information in a visual, graphical manner. Let's go to the next one. So this is, and fault tree would be referred to as sort of a top-down analysis. This guy, failure modes and effects analysis, for folks listening who are involved in risk management and product design and development, you'll be familiar with this technique as sort of a standard part of the risk management effort. This is a bottoms-up approach. So failure modes and effects analysis looks at a system, breaks it down into its constituent elements or components, and then asks, how could each element fail? What could cause it to fail? How would it fail? What would be the consequence of that failure? How would it affect the system? And looking at each element and how it can fail in a very detailed bottoms-up kind of way. So, thinking about our glucose meter potential failure, right? If one were to do an FMEA analysis of that glucose meter, you would look at those key elements of that system. You've got a sensor, you've got a sample acquisition method, you've got analysis that's done, you've got a user interface, you probably have a battery, right? All of the different elements. How might each of those fail in a way that leads to an undesirable result? So a useful tool, often in the case of root cause analysis on an existing product, you might have an FMEA that exists in the risk management file, but you may learn new things about potential failure modes that can happen with that system that might cause you to go back as part of the CAPA process to update that FMEA. So it's important to think about, when you've completed the root cause analysis, there may be elements of the design history file that could benefit from being updated. Okay, so what can go wrong with this process? Typically there's a lot of data to analyze. It's human nature that if you think you found the cause, you want to declare victory, but if you haven't sort of analyzed all of the possibilities, you might not have identified the actual cause. So it's important to be thorough, not stop too early. At the same time, again, as we talked about before, there's a risk of spending too much time analyzing, paralysis by analysis, as folks would say. So again, there's a judgment in terms of being thorough, but not, not getting bogged down, right? Making sure that you've got correct data that's leading to correct conclusions, not incorrect conclusions, and then it's particularly making sure that any bias or sort of preconceived notions don't get pulled through. So again, this is, like we said before, it's the discipline and the impartiality that's important to have the process produce accurate results.
Yeah, so once you've identified, you've got a list of potential causes, the next step is you want to have a way to evaluate or test them, rule out the theories that aren't supported by the facts, promote theories that do seem to be corroborated by facts and further testing. So the next phase is to test the potential causes. During this process, it's common to find that you need additional facts. So it's very often to iterate with previous steps to gather more information, or to set up tests to help you support or refute the theories. One of the things to be aware of in this process is that there's a tendency to kind of favor the easier causes. So you want to definitely go into this process being careful not to play favorites with your theories. One of the tools that we like to use in this phase is what we call the support refute matrix. So in this matrix, you list all your potential causes. You basically, it helps you ensure that there's a logical progression that fits the facts. You list the facts that support each potential cause, list the facts that don't support the cause, and then you can brainstorm ways to challenge the theory through testing to further support a theory or refute it, and then identify if there's additional documentation or research that might help shed additional light on a different theory. This matrix also allows the team to you can expand to include like a rating of probability, so that you can rank these causes as in terms of their likelihood to be the root cause, and it also helps you start identifying corrective actions or process improvements that would address each of these causes. So what do you do when there's no single clear root cause that emerges from this process? This is actually common. I think first you take a look to see if there's a likely benefit to gathering more facts. Maybe there's more resources that people that you could talk to, information that you could gather from academia or industry. So you have to take a look whether that's likely to shed light on either the causes you've already identified or maybe suggest new causes. If not, then it's, what you can do is determine corrective actions that cover all of the potential causes that can't be refuted. This involves risk, so this is not a path forward that you want to take without sort of a management level decision. So what can go wrong with this process? The main thing that I see at this stage is in terms of just not consciously biasing the weighing process, but you need to be very careful not to predispose this process to sort of bias caused by either cost issues or complexity issues. You don't want to try to like pre-screen these potential causes. At this stage, you want to identify the causes, even if they're costly, because that's going to allow a later full cost benefit analysis to be performed. You also need to be careful at this phase because there's a tendency not to want to confirm a cause if it assigns blame. You need to be sensitive about blame, be careful about the language that you use, but be forthright in documenting the cause in a factual manner. The next step that is very important is sort of a critical review of the root cause. And it's always good to get a cold body independent review of the work that the team has done. The work should make sense to a cold body reviewer, and this process helps discover blind spots. I would say one of the dangers of going through a root cause investigation is, especially if at the outset you feel like you know the root cause, but you're obligated to go through this process, there can be a tendency to kind of almost use it as just sort of a box checking exercise. Yes, we went through the process to confirm our initial beliefs. This critical review stage is, I think, the most effective way of identifying if that's happening. So you really do want to get a good independent review. So you want to ask for thoughtful reviews, get the right experts to take a look at the work that you're doing. Don't be intimidated by them. You want to invite scrutiny. And this is the best way to make sure that you've covered everything. So again, this process doesn't work when the team is just perhaps going through the motions. So by inviting that kind of scrutiny, you can ensure that this doesn't happen. This is also a good way of determining if there's additional facts that you need to uncover. And it's a good point to document the results so far so that you can give it to the reviewer, and you also want to document the results of that review. So the next stage is when you would move your findings over to the corrective action process. One thing to keep in mind, the corrective actions should be broader if there's lower confidence in the identified root cause. So where you're not completely sure of the root cause, you may want to have corrective actions that cover the root causes that you haven't been able to refute, or maybe that have a broader scope so that you have a higher probability of addressing the issue. With your corrective actions, you do want to target the causes and not the symptoms, and with an eye to both driving improvement and preventing recurrence. So documenting the results. Please remember to document your results. So remember when we first started gathering facts, we talked about that. One of the first steps of the process is to review past failures. So if you don't document the results of this root cause analysis, the next root cause analysis may end up, basically duplicating all of the efforts that you've done on this one. So you want to, write down your description of the problem, document a summary of all the investigation that you performed, the interviews, the tests, your matrices, any of the tools that you used to organize your facts or to sort through and evaluate the potential causes. You want to document the root cause, including the mechanism of failure if that's known. especially if it's a complex failure mechanism, and then turn that over to the CAPA process with suggestions for corrective actions, specific actions, and then any CAPA process would drive that to conclusion with verification of effectiveness. So here's an example timeline for a root cause analysis. As you can see, they can be pretty complex. It's a good idea to establish and maintain a schedule for your efforts. In most organizations, you will be asked probably quite often where you are in your schedule and plan to completion. And to do them right does take time. Sustained engagement is required. So having setting a timeline at the outset helps set expectations, and then revisiting it is a good idea to see where you are on track and when you may need to report out a change to that schedule. So that is what we had today on root cause analysis. I'm taking a look at the group chat. Don't see any questions, but I invite people to ask any questions they might have at this time.
Sure, and you can also feel free, you see our contact information here. Feel free to reach out to me or Lanessa afterwards if you'd like to chat about what we discussed today, and if you have any follow-up questions. As I mentioned on the chat, if you'd like a copy of these slides, we'd be happy to share them. Please just shoot me an email, and we'll get back to you. How about that? We landed the plane right on time here, a couple minutes early at the gate. So thank you, Lanessa. Rachel, thanks so much for having us on this morning.
Thanks for joining us, everyone. Have a great day.
Okay, bye-bye.